Longitudinal car-following models are the foundation of microscopic traffic analysis. The mathematical equations predicting how one car responds to another dictate the accuracy of everything from string stability to the way shockwaves propagate through a highway network. Recently, the field has seen a broadening range of modeling techniques. Researchers are moving beyond classical physics-based equations to implement data-driven algorithms, including deep learning architectures like LSTMs. This diversity has contributed to a reproducibility crisis. Because studies often rely on fragmented datasets, inconsistent data splitting, and heterogeneous preprocessing, it is difficult to compare results across the literature. Many current evaluation methods optimize for low one-step error on local datasets. This can lead to researchers confusing experimental overfitting for genuine methodological progress. Without standardized out-of-sample testing, it is difficult to determine if a model has truly captured longitudinal control laws, or if it is simply reflecting the measurement noise of a specific data source. OpenCF is a standardized benchmarking framework designed to decouple model development from evaluation logic. The framework is built on a massive dataset of 32,559 unique human-following human events. These trajectories were extracted from the onboard LiDAR and radar sensors of Waymo vehicles. Using onboard sensor telemetry provides a higher degree of precision than legacy infrastructure datasets like NGSIM, which often struggle with camera-based trajectory drift. The system operates as an evaluation-as-a-service pipeline. Researchers submit their model outputs via GitHub Actions, which automatically triggers a script to grade performance against a hidden test set. By utilizing server-side execution against identical, unseen data, OpenCF makes it easier to identify dataset-specific overfitting and ensures that all models are tested under identical conditions. This chart shows the distribution of longitudinal acceleration in both training and test sets. OpenCF applies the same rigorous filtering to the 83-hour training and hidden test set. The histograms demonstrate a high distributional consistency, with both profiles centered at 0 meters per second squared. To evaluate a model, the framework provides the observed states of the follower vehicle over a 3-second history horizon, sampled at 0.1-second intervals. This initialization window allows researchers to use past information for calibration or to initialize the hidden states required by recurrent neural networks. The prediction task begins exactly at the 3-second mark. This rigid boundary ensures that performance is measured purely on generated, open-loop prediction dynamics without data leakage. Standard deterministic metrics penalize valid behaviors simply because they deviate from a single ground truth trajectory. To account for human driving stochasticity, OpenCF allows up to 6 plausible paths, identifying the path with the minimum average displacement error to find the best match. This distinction separates short-term accuracy at the start of the prediction from the long-term trajectory drift that often accumulates in open-loop simulations. Beyond geometric accuracy, the framework monitors safety by tracking collision rates. A collision is flagged any time a follower's predicted position exceeds the leader's actual position. Combining long-term displacement errors with collision monitoring ensures that models cannot achieve high accuracy scores by ignoring basic kinematic constraints. The third dimension of the benchmark is naturalistic behavior. Models calibrated solely to minimize geometric error often produce robotic movements, failing to replicate traffic heterogeneity. To measure human-like behavior, OpenCF analyzes state transition probabilities across relative speed and spacing. After dynamically selecting unbiased bin widths, it calculates a geometric mean probability for each trajectory. A Mann-Whitney U-test then determines if the generated sequence matches natural human driving. Failing this statistical test suggests that a model's generated dynamics belong to a different distribution than human driving, which may limit its effectiveness for high-fidelity microscopic simulation. To establish a performance reference, 6 classical physics-based models were calibrated to minimize error across acceleration, speed, and spacing. These baseline results highlight a significant trade-off in current modeling. While models like IDM and the Gibbs model achieved 0% collision rates, they also showed the highest levels of long-term trajectory drift. These models favor kinematic safety because they are built on specific braking and stopping distance formulations. On the other hand, variants of the full velocity difference model achieved much higher short-term accuracy and lower trajectory drift. However, these gains came at the cost of safety, with some variants resulting in collision rates as high as 1.8%. The empirical data shows that these classical physics-based models often struggle to balance open-loop trajectory accuracy with physical validity. The naturalism analysis revealed the most consistent weakness among the baselines. Only 3 out of the 18 baseline variants passed the p-value threshold, indicating that traditional calibration objectives often fail to capture human driving heterogeneity. Currently, no baseline model achieves top-tier performance across the triad of accuracy, safety, and naturalism simultaneously. OpenCF provides the infrastructure for researchers to bridge this gap using hybrid or modern data-driven architectures. You can scan the QR code to access the standardized Waymo dataset and submit your models to the automated GitHub Actions pipeline. Benchmarking under these identical conditions is a necessary step toward achieving more reproducible results and fostering progress in traffic flow analysis.